Okay, g'day, I'm Jacob from Make Science Fun. Thanks for joining me today. Now, warning, today's video is going to be pretty serious, totally unlike most of the videos I put up on YouTube. Last week I did this video where I burnt this plastic pen and I'm dripping it, boom, 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 boom. It was like napalm sort of thing. I thought it was pretty cool, but I got all these negatives, downs and that thumbs, and I'm thinking, oh dear, I better do something a bit more serious, otherwise I'll lose all my fan base, nobody will want to come and watch. So today I'm going from burning plastic pen to determining the magnetic permeability of free space. So I have not actually practiced it or done the calculation or anything like that. So I'm excited to try and do it and to see if my value gets anywhere near the accepted value published of the permeability of free space. What is the permeability of free space? It's like the ability of a vacuum to create internal magnetic fields. It's to do with the properties of magnetism in a vacuum and how magnetic, I guess, a substance is. And so first a little bit of a background. I've got a bar magnet here with two neodymium magnets on either side. So I've got a north pole and a south pole, and the magnetic field lines emanate out the north and go to the south. You can represent the field lines using your fingers, so they're sort of doing these things. And up here on the balance, on the electronic scale, I've got this brass rod sitting on a piece of wood. So it looks something like that. It looks something like that, right? But it's a bit shorter. And the reason I'm using a brass rod is I need a very, very straight conductor. And I'm going to turn on the power pack, which is 12 volts, but I've got a variable rheostat here. And at the moment, I'm not getting any current whatsoever. There we go, now I am. Just need a little bit of a wiggle. I've got 8 amps flowing through here, 8 amps flowing through here. And so the magnetic field lines, here's the north pole, are going that way, and the current's going that way, my thumb, right hand push rule, then it should experience a force down when I bring in the magnet. So let's have a look. And look, that lights up because it's recognised that there's a force. It lights up, and look at that. It's recognising that it's like 0.6, whoa, all the way up to 1 gram of force. So there's a force due to the interaction of the magnetic field lines. Whoop, that's just clicked out because it's got too much current. I might just turn that off for a tick. But basically, there's a force because the current, which is moving, experiences a force in the magnetic field perpendicular to the direction of the current and the direction of the field. So if I turn it back on, you can see that the north pushes it down, but then if I rotate the magnet, and now the south is that way, the current's going that way, it should actually go negative now. It should go negative. And look at that, it does. It goes negative 1 gram. The current is producing a circular magnetic field around it. And so what I'm going to do is I'm going to bring another parallel conductor above it like that. And it's going to have also current flowing through it. And so the magnetic field produced by this conductor will affect the magnetic field produced by that conductor. And the two will repel. And then we're going to get a few values, and I've got an equation for the force per unit length between two current carrying conductors and the distance between them, and we're going to use that to determine the permeability of free space. So I have to set it up, and so somehow I have to have that sitting just above it, not touching it, just above it. And so I've got some wood here, just some pieces of wood that I'm going to pop here. And here, got my hot glue gun, and I'm going to hot glue a piece of wood there like that. And hot glue this one into position, like that. It's nice and firm. And then I need to get this rod. This is my parallel conductor, and it's going to get glued there, and it's got to sit just above, like 1 millimetre. Okay, nice and close, but I don't want it to touch. Don't want it to move either. So there we go, that's going to be sitting there, like that. So that's parallel. So I've got a conductor that way and a conductor that way, and when current flows that way in the top one and that way in the bottom, they're going to repel. And so they've got a length and they've got a distance between them, and hopefully going to experience a force of repulsion. And that force of repulsion is equal to mu naught, which is the permeability, magnetic permeability of free space, times I1, I2, times the length over 2 pi r. And so I'll know I1, I'll know I2, I'll know the length, I'll know 2 pi and I know r. And so I'll also know force, because I can read it off the scales, and so the only unknown will be mu naught. Okay, so I've got it wired up, and current's about to go that way through one, that way through the other, and I'll read the ammeters. Here we go. I've got 11.2, 10.4, and a reading of 0.09 grams. Wow, that's not much, is it? Now I'll really try and do a short circuit. Let's see what happens. Here we go, tear it. And boom. Okay, it's gone up to 0.18, and the current on that one was 14, and the current on that one was 15.5. Okay, so let's calculate mu naught now. Here's the top conductor carrying 14 amps, the bottom conductor carrying 15.5 amps. They're 0.5 millimetre apart, they're 95 millimetres long. The force between them was 0.18 grams. And here's the equation. The force is equal to the length times the permeability constant times I1, I2 on 2 pi r. Okay, let's rearrange it to make mu naught the focus of the equation. So multiply both sides by 2 pi r, so we get F times 2 pi r, and then divide both sides by the length, and I1 over I2, that should be a 2 there. And now there comes mu naught. And so let's sub in some values. The force is equal to 0.18, but we need to divide that by 1,000 to times it to get it into kilograms, and then times it by gravity to put it into weight, times 2, times pi, times the distance between them, which is 0.5 times 10 to the minus 3, over the length, which is 95 times 10 to the minus 3 to put it into metres, times 14 times by 15.5. And let's put that into the calculator. Excuse me, engineering. Here we go. 269 times 10 to the minus 9, which is equal to 2.69 times 10 to the minus 7, and the actual value of mu naught is equal to 12.6 times 10 to the minus 7. So I'm well within, well that's pretty close. In terms of the order of magnitudes, pretty close for a little bodgy experiment like using brass tubes and dodgy ammeters. I told you it was going to be a bit more serious today. So thanks for joining me in finding the permeability constant and the magnetic permeability constant of free space. And hopefully I might see you next week. Okay, bye for now.